Hello and welcome to lecture 11 of the course Computational Complexity. In lecture 10 we saw CoNP, which is a class of all languages whose complement is an NP. And in other words, it's also the class of all languages such that that are characterized by the universal quantifier. For all y, all strings y, the verifier machine should accept x and y, right? So these are the two characterizations of CoNP, and today in this lecture we are going to see how this notion can be generalized to form a hierarchy of sorts, right? So this hierarchy is called polynomial hierarchy. Okay, so let us try to take it to the next level, right? So what do we have here? For NP we had this thing which is the existential quantifier, right? There exists. For CoNP we had the for all. Now can we kind of combine these, and in what way can we combine these, right? Let's see. Right. So now we will define two classes called sigma 2 and pi 2. Sometimes it's also called sigma 2p and pi 2p because eventually everything has a polynomial time verifier going on, right? So what is sigma 2 and pi 2? Sigma 2 is a class of all languages such that x is in the language L if there is a string y such that for all z, a verifier will accept x, y and z, right? So this may seem a bit confusing now, but hopefully with some examples we'll clear this, right? And pi 2 is the opposite. It's a class of all languages L such that x is in L if and only if, right, for all y there exists z such that the length of y, length of z are polynomial in the length of x, and there is a verifier that accepts x, y and z. So the main difference or actual difference is in the order of the quantifiers. So here there exists a y such that for all z something should be true. Here for all y there should exist z for which something is true. So this order of quantifiers is important. So let me just illustrate that. Maybe over here. So consider this. Let's say a, b, c, etc. are natural numbers, right? There exists a such that for all b, a is greater than b. Is this true? Does there exist an a such that for all, let's say a and b are natural numbers. Does there exist an a such that for all b, a is bigger than b? No, right? Once you fix an a, or there is no number that is greater than any b that you pick, right? So this is not true. This is false. But what if we swap the quantifiers, right? For all a, maybe I'll change the color again. For all a, there exists b such that a is greater than b. This is true, right? Because if you pick any number a, you could simply pick a b that is smaller than that. So here the thing that is happening here is that the order of quantifiers. First you want an a that is bigger than all the b, and in the second you want an a, or for you pick the b after you pick the a, right? So you can choose whatever a you want and then you can pick the b, right? Or rather, if you see it as a two-player thing, right? So let's say I pick an, so in the case 1 I have to pick an a such that for all b it has to work, and in case 2 I will pick, or we need to pick an b that should work for all a, or that need not work for all A, the choice of B happens after A, right? So this is why 2 is easier than, or 2 is true and 1 is false, or the first one is false and the second statement is true. So what I'm trying to illustrate here is that the order of, so these may look similar, but it's not similar because the order of quantifiers matter. And here I give you an example, a simple example where the order of quantifiers do matter, right? So you may see why that is the case, right? So this is sigma 2 and pi 2, right? Sigma 2 is where we have their axis followed by for all, or the universal quantifier, sorry, existential quantifier followed by the universal quantifier, and in pi 2 we have the universal followed by the existential. Now one simple fact to see is that P and P co and P, they are all contained in sigma 2 as well as pi 2, right? So just for simplicity we'll just show this. Co and P is contained in sigma 2. How does one show anything is contained in any other thing? We show that A is contained in B by taking an arbitrary element of A and then showing that this element is present in B. So we take an arbitrary language L, right, which is in co and P. Now we want to show that this is contained in sigma 2. So what does this mean? L is in co and P. This means that there is a verifier characterization such that is what is written here in red. For all, if X is in L, for all Y, the verifier should verify that X is in, verifier should be able to accept X and Y, right? There should be a verifier such that for all X, or X is in L if and only if for all Y it accepts. So even if one Y does not accept, then X should not be in L, right? Now this is the verifier. Now I could run the verifier with another input, a dummy input, which does not really change the outcome of the verifier, right? So I could define V prime, right, V prime as a verifier which takes Z also as an input. So remember, Z is a dummy input. So V prime X Z Y is simply defined as V X Y, right? Which means that if you get V prime gets X Z Y and as inputs, it just simply runs V on X and Y. It just ignores Z. So it doesn't really matter what Z is. And since it simply runs V is deterministic polynomial time because L is in co and P, and that's why we got V. Hence V prime is also deterministic and polynomial time. Sorry. Right. Now we can say this, X is in L if and only if there exists Z such that for all Y, V prime X Z Y equal to 1, right? This is true. This is true simply because Z simply does not matter here. V prime X Z Y will actually be, this will be simply V of X Y, which is what I have written over here. So V prime X Z Y will simply be V of X Y. So the existential quantifier for Z doesn't really come into play because this is true. Finally, whether V prime X Z Y is equal to 1 or not only depends on X and Y. It does not depend on Z. Hence, now we are able to write, but then this statement that is underlined over here, it's characterizing L in the form of a sigma 2 language, right? So I have their X's followed by for all. So simply co and P is in sigma 2. So basically co and P has this characterization for all. We needed a there exists, so we put the there exists by a dummy variable. Similarly, we can do co and P is in pi 2 by adding another dummy variable, right? So this is not something very similar that I'm not going to get into. So in pi 2, we will need to add the dummy variable after the for all, right? Because pi 2 means for all followed by there exists. So the pi2, the dummy variable z should be added after the for all, but the rest is very similar. Maybe this is something simple. I'll just renumber it. Show that p and np are also contained in pi2 and sigma2. This is not very difficult. You could directly, to show, you could add two dummy variables y and z. Or I just showed np, co-np, right? So np is very similar. We'll just need to add the dummy variable for all, and for p we will need to add two dummy variables. But we don't need to get into that. We could just use we don't need to do the proof again from scratch. We could just use the result that co-np is in sigma2 to infer that p and np are in sigma2 and pi2. For instance, let's say, to show that, maybe I'll just show one thing. Suppose, so we want to show np is in sigma2, right? Suppose L is in np, right? This means L complement is in co-np. This means, so we want to show L is in sigma2, but we've already seen that L complement is in co-np, which is in pi2, right? And so this implies that L is in sigma2. If a language is in, so again, this is something that we will see soon. A language is in sigma2 if and only if the complement is in pi2, and a language is in pi2 if and only if its complement is in sigma2. This should not be that difficult to see given the way these languages are characterized. So L complement is in pi2 if and only if L is in sigma2. So this means NP is contained in sigma2. Similarly, we can prove NP is in pi2, and P is we already know that P is contained in NP and co-NP, so the other part also follows. Now some examples. One is not smallest formula. So for instance, what is a not smallest formula? So x1 and x2, or x1 and x2 complement. So when will this be true? So this is true whenever x1 is true, and this is false whenever x1 is false. And you can verify that this is just another way of writing x1. So we will give a Boolean formula as input, and we are asking whether this is the smallest way to represent that Boolean formula. So anything that is not the smallest formula will be a S instance. So if you give the first one x1 and x2 or x1 and x2 complement, it will be accepted. Okay, so the claim is that this is in sigma2. Why? Because how do we write this thing that this is not the smallest formula? Okay, so a Boolean formula phi is not the smallest Boolean formula if it's a Boolean formula, and there exists another formula psi which is equivalent, right? Psi is smaller than phi, and this is equivalent. Equivalent means for all the values it evaluates to the same value, right? So if you consider this and this, the thing that I have written in red, they are equivalent. For all the values of x1 and x2, it is equal to just x1, right? So phi is a not smallest formula, NSF, if for all psi, right, for all the formulas, there exists a formula, right, when is it a not smallest formula? If there is a smaller formula that is equivalent. So there is a smaller formula of psi such that for all inputs x, phi and psi are same, and moreover psi should be smaller than phi in size. So two things. One is that psi should be smaller than phi, and for all x you want phi and psi to evaluate the same. So this is the logical representation of phi being in NSF. So now you can see why it is in sigma 2, because for all the formula psi, there exists a formula psi such that for all x these two conditions have to be satisfied, and these two conditions can be polynomially verified. Once psi is fixed, phi is fixed, and x is fixed, this is very easy to check. Psi's can be easily verified, and if you can evaluate phi and psi at x and check whether they are equal, right? For a fixed psi, phi and x, it's easy to check. So it's a polynomial verifier, and this implies that ns not smallest formula is in sigma 2. Now I mentioned that if a language is in sigma 2, the complement should be in pi 2, and if a language is in pi 2, the complement should be in sigma 2. Just to illustrate that, and also to give another example for a language in pi 2, let us consider the complement language, which is the is smallest formula, right? So given a Boolean formula, we are asking whether it is the smallest representation of that formula. There is no equivalent shorter formula. So how do we state that? Phi is the smallest formula if, so when is something the smallest formula? Whatever smaller formula that you consider should not be equivalent, right? So for whatever smaller psi that you consider, it should not be equivalent. In other words, if you consider a psi, if it is smaller, it should not be equivalent, or it should be bigger, right? So either it should not be equivalent, or it should be bigger. So, or it should be the same size. So one way to write it is the size of psi, either it is bigger than the size of phi, right, or phi x is not equal to psi x. So again, there exists here. For all the psi, there exists x such that either phi is bigger, either psi is bigger, or there is an x such that phi and psi are not equal at that x. So the second part, the red underlined part, ensures that they are not equivalent. Either they are not equivalent or psi is bigger. So this is a pi 2 representation, because the for all quantifier comes before there exists quantifiers. The universal quantifier comes before the existential quantifier, right? So this is the pi 2 language. Is smallest formula is in pi 2, and you can see that is smallest formula and not smallest formula are complement languages. If it is the smallest formula, then if it is not the smallest formula, it's a negation, right? And there's another illustration to show that anything that is in pi 2, if you take the complement, it is in sigma 2, and vice versa. That is what I have written here in other words, that pi 2 is co-sigma 2. Again, so what do I mean by co? So a class x and the class co-x, right? So this is a standard notation, is a set of all languages L such that L complement is in X. So again, X, we have already seen NP and co-NP. What I am saying here is, in this sense, pi 2 is co-sigma 2 and sigma 2 is co-pi 2. This does not mean, this is again caution, co-X does not mean the complement of X. Okay. Again, what I mean here is that L is in sigma 2 if and only if L complement is in pi 2. Another language is exact clique, right? So remember, clique was that it's a graph G and a number k such that G has a k size clique. Exact clique is different in that G has a k-size clique, and that is the largest clique. So if I had given this as a instance of clique, right? And so if I give G comma 3 as an instance, it will be S instance for a clique, but it will not be S instance for an exact clique because there is a clique of size 4. Right? So exact clique requires us to be the K to be the largest clique in that graph, size of the largest clique in that graph. Now show that exact clique is in sigma 2. So you have to write it. There exists a clique of size k, and for all sets of size bigger than k, there is no clique. Right? So this is what the rough high level idea is. You can try to figure out how to write it in a logical sense in a way that is verifiable in polynomial time. Okay, this is something that I've already mentioned. The order of the quantifiers are important. You cannot swap the order of quantifiers. So I mentioned here the example A and B. Right. So if the order is changed, the truth false value itself may change. Right. So now an important theorem. Suppose P equal to NP. Then P and NP are equal, and co-NP is also equal, and sigma 2 is also equal, and pi 2 is also equal. So everything becomes equal to P. In lecture 10, I gave you the high level idea of why P equal to NP means P equal to co-NP as well. Right? So we have already seen P equal to NP means P equal to co-NP. I think in lecture 10 we stated P equal to NP implies NP equal to co-NP, but then when P equal to NP and NP equal to co-NP, it also means P equal to co-NP, right? Now consider, now we have to show that when this is the case, P is equal to sigma 2 also, right? Again, P is a subset of sigma 2. We have to show that sigma 2 is equal to P. So what can we do? We can take a language in sigma 2 and show that it is in P, right? So consider X language L in sigma 2. Now what does it mean? It means there is a for all, there exists for all characterization, right? First there exists and then for all by for all. Such that X is in L if and only if there exists Y such that for all Z, this is true, right? So I can write it like this. Now I can just reorganize slightly differently such that xy is in L prime if and only if for all z v x y z equal to 1. Okay, so it's same thing, but I have taken y over here and considered a language of two tuples x comma y, and now I can consider this as a two tuple. So now what does it mean here? So xy is in L prime if and only for all z this is equal to 1. So now think of xy as a one singular unit here. Now L prime looks like again V is a polynomial time verifier, so L prime looks like a co-NP language, right? So it's a for all characterization, for all quantifier. So L prime is in co-NP. By assumption, we have already assumed that P equal to NP implies P equal to co-NP, which means L prime is in co-NP means L prime is in P, which means that for L prime there is a polynomial time decider, deterministic polynomial time decider. So when x comma y is in L prime, then there should be some V prime that should be able to verify it without any quantifiers or anything, right? So V prime xy is equal to 1. Now let us try to plug things back in this, right? So V prime xy should be equal to 1 is what I said, right? So now let us try to plug things back. So xy is in L prime if there has xy is in L prime if this is the case. Now I can write it as x is in L for all, sorry, there exists, if and only if there exists y such that, right, now instead of this thing I can just have a single um, sorry, I think my so the thing is that this role of z is gone because xy is in L prime just has a deterministic verifier, right? So I don't need this z now, so I can just replace it with, maybe I'll use another color here. I'll just replace it with v prime xy equal to 1. So all that we have is there exists y such that v prime xy equal to 1, right? Which is what I've written here. Which means now it's an NP type characterization. It's just an existential quantifier, which means L is in NP. So we started with the assumption that L is in sigma 2, and when we've reached L is in NP, by assumption NP is equal to P. So which means L is in P, which means sigma 2 is contained in P, and the other direction is easy to see. We have already, I think, mentioned that, which means P is equal to sigma 2. And similarly, you can show P equal to pi 2 also. So what does it mean? Just to give a high level, let's take a step or two back. It means that if P equal to NP, then co-NP also is equal to P or NP. Both of them are equal. Sigma 2 is also equal to P or NP, and pi 2 is also equal to P or NP. Right? So maybe just 1 second before we proceed. So just let us try to see how P and NP are, P and P, sigma 2, etc. are located. Right? So it's like this. So we know that P is contained in both NP and co-NP. However, we do not know whether NP and co-NP are the same. Right? Both of them contain P, but there are things in NP which is not in co-NP, or which is not known to be in co-NP, and vice versa. Things in co-NP that are not known to be in NP. Now you can consider sigma 2 as containing all of this P, NP and co-NP, and pi 2 also contains P, NP and co-NP. But then sigma 2 and pi 2 are not comparable. We don't know whether sigma 2 is contained in pi 2 or pi 2 is contained in sigma 2, right? In fact, if you show that sigma 2 is contained in pi 2, that would mean pi 2 is also is equal to sigma 2, in fact, because their sigma 2 is co-pi 2, right? Right? So the thing I want to say here is that, yeah, so this is the current situation. And another result which is very similar, which I will not go through in detail, but I'll just tell the statement. Suppose, so here we said that if P equal to NP, then everything sigma 2, pi 2, everything co-NP, all of them become equal to P. Now let us say NP is equal to co-NP. I don't say anything about P being equal to NP or not. Let's say NP being equal to co-NP. So it could be something like this. This is P, and this could be NP as well as co-NP. Now in such a case, what we are saying is that sigma 2 will be equal to NP, and pi 2 will also be equal to NP. The proof is along very similar lines. Nevertheless, I have written it down. Just that over here we use L prime is in co-NP implies L prime is in P. Here we cannot use that. We will say L prime is in co-NP implies L prime is in NP, and NP will give you a there exists quantifier. So combining the two there exists quantifier, we'll be able to show it is in NP. So you can work out the details. So the point is that if P is separate from NP, but NP is equal to co-NP, then everything sigma 2, pi 2, everything will collapse to this point, right? And like this, we can define a generalization of sigma 2 as those languages for which we have a k level quantification, right? Sigma 2 is like there exists for all, right? So sigma k is a k level quantification starting from there exists, then for all, then there exists, then for all, and so on. And the last one, qk, it's a quantifier depending on the parity. If k is even, it will be for all. If k is odd, it will be there exists, and followed by a polynomial time verifier. Similarly, pi k consists of k quantifiers, k alternating quantifiers, such starting with a universal quantifier, that is a for all, right? Again, it's important that these quantifiers alternate, because if the quantifiers are the same, let's say like there exists followed by there exists, then you could just combine them into one quantifier, right? So to get the full power of these quantifiers, it should be alternating. And just to conclude, so in this definition, right, so I just defined sigma k and pi k. If you look at sigma 1, it is nothing but np, because when k equal to 1, you just have single existential quantifier in sigma k, which is corresponding to what we have seen for np. And similarly, pi 1 corresponds to co-np. So sigma np is actually sigma 1. And co-np is actually pi 1. So you can see how these classes line up, or at least as far as we know now. P is contained inside sigma 1 and pi 1, which are not comparable. P sigma 1 and pi 1, or P, NP and co-np are all contained in sigma 2 as well as pi 2, but they are not comparable. All of these classes, P, NP, co-np, sigma 2, pi 2, are all contained in sigma 3 and pi 3, but they are not comparable. And we can draw another layer like sigma 4, pi 4. They will contain all of these, but they will not be able to say one is contained inside the other, sigma 4 and pi 4, and so on. Sorry. So this is true for any I. Sigma I minus 1 is contained in sigma I and contained in sigma I plus 1. It's also true that pi I minus 1 is contained in sigma I and sigma I is contained in pi I plus 1. But for any same I, sigma I and pi I are incomparable. And these set of classes together are called the polynomial hierarchy. It is a set of all sigma k, pi k, everything together are called polynomial hierarchy. And what is interesting is that if p equal to np, right, we already saw that if p equal to np, sigma 2, pi 2, everything become equal to p. But what we are saying is that if p equal to np, then the entire polynomial hierarchy collapses to p. That means all sigma 3, sigma 4, sigma 5, everything, pi 2, pi 3, pi 3, pi 4, pi 5, everything collapses to p. Similarly, if np equal to co-np, I am not saying anything about p being equal to np or not, then everything collapses to up to np, right? Polynomial hierarchy collapses to np. If let's say p is separate from np, co-np, np is separate from sigma 2, etc. Let's say at sigma 10, below sigma 10 everything is separate, but at the 10th level sigma 10 is equal to pi 10. Then everything above will collapse to sigma 10, which is equal to pi 10. So if sigma k equal to pi k for any k, this could be 10th or 12th or anything, or it could be even second or something, or third or something, right? Whichever position, then the polynomial hierarchy will collapse to that level, that kth level. Sorry. I missed one small point in the notes, which is the definition of the complete language, which I will maybe briefly describe in the next video. Thank you.
Swayam Prabha, Digital India, Educated India.
Hello and welcome to lecture 12 of the course Complexity Theory. So in this will be a rather short lecture. I want to talk about some aspects of polynomial hierarchy that I wish to bring out, but that did not get emphasized in the previous one or two lectures. Okay, so we already know what is polynomial hierarchy, right? So what is polynomial hierarchy? It is starting from P, NP, co-NP, then sigma 2, sigma pi 2, sigma 3, pi 3, and so on, which I described in the previous lecture, right? It's this hierarchy of classes where and that there is a natural hierarchy that forms, and that is called polynomial hierarchy, right? So we have already seen P and NP and co-NP. So NP, just to remind you, are the class of languages that have a deterministic polynomial time verifier, meaning to check L is a language in NP, then for all X that is in L, there is a short certificate and a verifier can verify the certificate, right? The verifier is deterministic. And if L is in co-NP, then there is a verifier, whatever certificate you give, it must be able to verify it, right? So X is in the language if and only if there is a verifier such that it will accept all the whatever certificate you give, it should be S instance. And even if one certificate is not validated, is not able to be validated, then it will be a no instance, right? So there is this asymmetry. NP means you just need one certificate to be verified. Co-NP means you want all certificates to be to be verified. But even if one is not correct, then the language should not be in the language. Sorry, the string should not be in the language. And so here there is an existential quantifier in NP, and there is a universal quantifier in co-NP, right? And sigma 2, pi 2, etc. is taking this to the next step. And sigma k in general is k quantifiers, k alternating quantifiers starting with the existential quantifier, that is sigma k. Pi k is k alternating quantifier starting with the universal quantifier. Universal is for all, right? So we have up to k quantifiers, not up to exactly k quantifiers, but even if you have a subset of less than k quantifiers, that will be a subset of sigma k or pi k, right? That's what is shown in the figure here, right? K alternating quantifier starting with sigma is starting with their axis is sigma k, and for all is pi k, right? So now I want to bring out a couple of points. So one is that I mentioned that NP is a class of, or co-NP is a class of all languages whose complement is in NP. Co-NP is not the complement of NP itself. It is a class of languages whose complement is in NP, right? Let me explain. So sorry, L is in co-NP. If and only if L complement is in NP, right? Suppose L complement is in NP, right? So then what can we say? If L complement is in NP, then there is a polynomial time verifier, which means if X is in L complement, right, there exists Y. So L complement has a polynomial a deterministic polynomial time verifier such that length of y is polynomial in the length of x, right? And there is a deterministic polynomial time verifier v such that, or maybe I should say this is not specific to the x and y, right? Then there is a deterministic polynomial time v, okay, v is the verifier such that vxy is equal to 1. Right? So the v is just specific to the L complement. Now now consider so what about x that is not in L complement, right? So what is the negation of this? So suppose x is in L, right, which means x is not in L complement, right? X is in L complement, x is not in L complement. So even the right hand side we can negate. What is the negation of this? So I'm saying that there exists y is such that something is true. So the negation of this is there exists y such that something is true. So the negation of that statement is that for all y that is not true. Right? So it's like saying there are 10 students or 10 people, all of whom are right-handed, or what do I say? Let's say there exists a left-handed student in the class of 10 students. Right? The negation is that there is no left-handed student, all the students are right-handed, right? So similarly, there exists a y with a certain property. The negation is that for all y, the property is not satisfied, right? For all y such that y is in polynomial length of x, right? Vxy equal to 0. That means this is the same verifier that as before, right? So now we have a deterministic machine that outputs 0 upon certain condition. Now I construct let's say set v prime equal to complement of v, right? So you can run the machine v and then flip the output. If it accepts, you reject. If it rejects, you accept, right? So that is v prime. Now I could write the same thing, right? For all y such that length of y is poly x, v prime xy is equal to 1. So x is in L. So again, I bringing out this here. X is in L if this is true. So now this is exactly the description of the class CoNP. For all y such that y is poly x, vxy equal to 1. So here it's v is v prime. So it's another notation, but it is the same thing, right? So this is why this characterization makes sense. So if it's like satisfiability is like, does there exist a satisfying assignment? Tautology is the so if the assignment is not satisfiable, then whatever you plug in, everything evaluates to false. Now if I somehow complement the formula, right, I will get a new formula such that if the original thing was satisfiable, or if the original thing was not satisfiable, the new formula will be always satisfied. Right? So not satisfiable means it always evaluates to false. So the complement formula will always evaluate to true. So that's why if you take an instance, a Boolean formula phi, if it was not satisfiable, the complement of phi is a tautology, right? So again, that Hope that adds some more insight to what I said in the previous lecture. Now let me just explain the same thing in the context of sigma 2 and pi 2, or sigma 2 is we'll say L is in sigma 2 if and only if there exists a polytime verifier, polytime V, deterministic polytime V, such that X is in L if and only if there exists Y such that for all Z where Y and, so I am skipping this part about Y and Z being of polynomial length, okay. We just for brevity, V X Y Z equal to 1, right? So now what about the complement of this? So let us try to negate the left hand side and right hand side. X is not in L, right? That is a negation of left hand side. So we want there exists Y such that for all Z this is true. So what is the negation of this? There is a Y such that for all Z something is true. So there exists Y, so let us take it step by step. There exists Y such that something is true. So the opposite is that the negation is that for all Y that thing is false. So first step is for all Y this thing is false. Now what is this thing? This thing is that for all Z something is true. So now I want to negate that. So for all Z something is true means that the negation is that at least there should be one Z for which that is not true, right? So there is one Z for which there is not true. So one Z for which Vxy should not be equal to 1. So now like we did before, I could define V prime in such a way that V prime is the complement of V. So V prime is 0 if V is 1, and V prime is 1 if V is 0. So now we can that means we can rewrite this as for all Y that exists Z such that V prime X Y Z equal to 1. So now we have that X is not in L, so we will say that X is in L complement is another way of writing the same thing if this is true. But now this is exactly the characterization of pi 2. So hopefully this gives you an idea why pi 2 is the co-sigma 2. Right? So pi 2, in other words, pi 2 consists of all the languages whose complement is in sigma 2. Right? So we took a language L which is assumed to be in sigma 2, and then we saw that the complement is in L complement is in pi 2. This is what we have shown. Again, hopefully this gives you some insight to the structure of the polynomial hierarchy. Similarly, I'll just use another color. Similarly, pi k is co-sigma k, right? Because it's much of the same thing, right? You can do whatever we did for pi 2, you can do for pi k. So that is the first thing that I wanted to say. The second thing I wanted to say was about complete languages for sigma k. We saw NP completeness, we saw co-NP completeness. So let us see, does sigma 2 have a complete language, does pi 2 have a complete language, right? So the language that I want you to think about is what is called QSAT2, right? QSAT2 is so QSAT2 is a set of all Boolean formula with designated partitions on the variables, okay? So I will have some variables as part of one set and some variables as part of another set. So it could be something like this. Let's say x1 or x2 or y1 and x3 or x4, something like this, y2. So let's say a formula consisting of some x's and some y's. Now I want to ask this question: does there exist a way to set x's in such a way that, let's say, I get to set x, you get to set y? Now, is there a way that I can set the x's such that whatever you set the y, it will be true? So, can I fix some of the variables in such a way that, or there is some that is already demarcated to be my territory and given to me? Can I set some of the variables in such a way that whatever you set the remaining, the formula will evaluate to true? This is the language QSAT2. So the first class of the demarcated to me is denoted y1 here, right? And demarcated to you is given as y2 here, right? And I'm asking, does there exist a way to set y1? Y1 is a set of variables here. Okay, so it's a bit of a confusing notation, such that whatever you give to the variables y2, the formula will evaluate to true, right? So what is satisfiability in this kind of setting? Satisfiability is just, there is no two player, only one player. Given this formula, is there a way to set variables such that it is true? Now it's like a two-player thing. I am given some variables. Now, is there a way to set these variables in such a way that whatever you set in the remaining, it will evaluate to true? So that is QSAT2. In other words, it's I think quantified SAT2. Q stands for quantified. Maybe I'll just write that down. Right. This is a bit messy, so I'll just write it again. Quantified set. Quantified means this, there exists, and for all are called quantifiers. Quantified set. And 2 means there are two quantifiers, right? And this is clearly in sigma 2 because there is a for all followed by this thing which can be verified by a deterministic polynomial time machine, right? So once you give y1 and y2 a certain assignment, it's easy to verify that the formula evaluates to true. And since and this happens to be, this QSAT2 is a sigma 2 complete language. So again, we have not even defined sigma 2, but we can define it in exactly the same way that we defined an NP complete and co-NP complete. So what is sigma 2 complete? Just to define sigma 2 complete. Sigma 2 complete. So A is sigma 2 complete. A is sigma 2 complete. If A is in sigma 2 and for all B in sigma 2, B reduces to A in polynomial time. So again, we use the same reduction, polynomial time reduction. So sigma QSAT2 is certainly in sigma 2 because it is of the form, of the correct form, and verifying that a formula at a given assignment is true is something that is achievable in polynomial time. And it is also sigma 2 hard, so to speak, meaning condition 2, anything in sigma 2 can be reduced to that, because consider any language L in sigma 2, okay? Now if X is in L, by definition there exists Y such that for all Z, the verifier has to evaluate X, Y, Z to be true. Now the point is that this verifier, whatever this verifier does, can be encoded into some Boolean formula, right? At least maybe a length specific Boolean formula. That means that I have already, once instead of the verifier you have a Boolean formula, that is kind of the QSAT2 form. Right? So that's why that is the intuition of this. So QSAT2 is a sigma 2 complete language. Similarly, you can define QSAT-K, right? So, so just I will say a few more things. So QSAT2 complement is pi 2 complete. Just like we said, anything that is complement of NP complete is co-NP complete. We can say that anything that is complement of sigma 2 complete will be pi 2 complete. And similarly, we can define QSAT-K where we start with the existential quantifier and we have k quantifiers alternating. So here we have started with the existential quantifier in QSAT2, right? And there are two quantifiers, there exists and for all. But in QSAT-K we will have k such things, there exists for all, there exists for all, and ending in there exists or for all, depending on whether k is even or odd. So QSAT-K can be defined. And that will be the complete language for sigma k. This will be the complete language for sigma k. Right? So if you want to show that QSAT like sigma k is contained in, let's say, a smaller class, let's say P, you can just show that you can pick QSAT k and show that a polynomial time algorithm for it, a deterministic polynomial time algorithm for it. But again, QSAT k is something that is harder than SAT, right? Because SAT is just one quantifier, but QSAT k has k alternating quantifiers, and these are much more powerful, at least seemingly much more powerful, right? Finally, I just want to say one more thing, that this this polynomial hierarchy, it is so there are many levels, and as I said in the previous lecture, if let's say sigma 3 is found to be equal to pi 3, then everything above it will collapse to the level of sigma 3. If sigma 2 is found to be equal to pi 2, then everything above it will collapse to sigma 2 or pi 2. But it is believed that, so the thing is that we don't know if any of these are distinct. It is possible that all of them are equal to P. It's also possible that all of them are separate. Everything is different from every other thing. Sigma k may be strictly bigger than sigma k minus 1, which is strictly bigger than sigma k minus 2, and so on, right? So we don't know just like P versus NP, we don't know whether P is strictly contained inside NP or not. Any of this containment, we don't know whether it is strict or not, right? Because any of them, if any of them is proved to be equal, then many things collapse. So that's all I wanted to say in this lecture. So we saw why NP and co-NP are complement, or NP and co-NP, the characterizations in terms of the verifiers make sense. Basically, you take the characterization for NP and you take the complement of that characterization, you get the characterization for co-NP. And similarly, the same thing holds for even sigma 2 and pi 2 characterizations, and in general sigma k and pi k characterizations. Then we saw QSAT 2, which is a complete language for sigma 2, and generalized to QSAT k, which is a complete language for sigma k. And complement of QSAT 2 is a complete language for pi 2. And yeah, I think that's all I wanted to say in this lecture. And so we'll meet in the next lecture. Thank you.
Swayam Prabha, Digital India, Educated India.
Welcome to this lecture. In the last lecture, we had just started the proxy pattern. We had said that the proxy design pattern is a very important design pattern and very widely used. In almost every application, we will have opportunity to use the proxy pattern. Now, let us look at the details of the proxy pattern. Last time, in the last lecture, we looked at only the basic overview of the pattern. Let us now look at the details of this pattern. The proxy pattern, here the proxy has the same interface as the target object. The client uses the proxy and the proxy stores a reference to the target object. The client creates the proxy and interacts with the proxy. For the client, the proxy is actually as good as the target object. The client does not interact with the target object, it interacts with the proxy, but the proxy stores a reference to the target object, and any method invocation by the client and the proxy handles it if it can, otherwise it forwards or delegates to the target object or the server. Sometimes it does not just forward it or just make the method invocation on the server object, but also has its own wraparound code. It executes some code before calling the method of the target object, and also after the target object method completes, it might have some code to execute. In that way, the proxy might enhance the capability of the server object. So, here the proxy might have some wraparound code on the method of the target object. We can see in this diagram that the client interacts with the proxy. For the client, the proxy is as good as the client. The client has no idea or no knowledge of the real object. It interacts with the proxy thinking that that is the real object. The proxy in turn, for some simple queries that it can answer, it responds to the client. For the queries that it cannot answer, it forwards it to the real object. But one thing is that in many times in a network situation, the proxy is in the same machine as the client, and the real object is across the internet in some other machine. So, just drawn a rectangle over here saying that it is on the same machine. On the same machine, both client and proxy objects reside. The real object is on a different machine and possibly across the network. And for this reason, we call the proxy object as the local sit-in for the real object. Just like in a classroom scenario, a student who does not come to the class